Hello, class. Just want to make sure my microphone and everything is on. These last two lectures that we're going to have are going to be on two standalone topics that are very important to statics, dynamics, and strength of materials. And one of those is going to be thin-walled pressure vessels. And by thin-walled pressure vessels, what do I mean? I'm going to be talking about pipes, right? Isn't that what I really mean, is that we're talking about pipes? But I also want to talk about scuba tanks, because I'm going to do a example of a scuba tank falling off a ship over the Mariana Trench, or Mariana's Trench. I don't know. I think it's Mariana Trench, but we'll see. I've just made myself a cup of tea, but of course it's over there on the other side, and I don't really need it right now. So what I want to talk about, like I said, is thin-walled pressure vessels, and I think I've just lost them here. Now there they are. Okay. So I said before that I would explain this later, and here we are at the last two lectures. So I want to look at at two aspects of a thin wall pressure vessel, right? The first aspect is I'm going to look at, let's say that this is my half of my thin wall pressure vessel. We'll look at a scuba tank, right? And so we know that this distance here, I've exaggerated this a little bit, is going to be T. That's the thickness, right? Thickness of that cross section. And then let's look at the cross section, because the cross section has to hold back all the pressure, doesn't it? So we've got two different forces there. We've got one force that's due to pressure on the inside. This is my pressure force that's trying to push this apart, right? And then we've got the other forces around the outside in the steel that are trying to hold the two halves of the pressure vessel together, right? So let's look at what is the force that's pushing it apart. So the force to push it apart is going to be the pressure force inside. And we know that that the force due to pressure is just the pressure times the cross-sectional area, right? So let's write that out. So pressure times the cross-sectional area. Now, what is the cross-sectional area? Let's say that this is a very thin thing. Really what we have is something that would look more like a cross-section. I'll draw the cross-section a little bit bigger. That would be just a very thin wall, right? So even though the radius of a scuba tank might be 8 or 4 inches, the wall thickness is only about 1/4 of an inch, okay? So it's only about 1/4 of an inch thick, and that's how I probably should have drawn it here too, but you know, you get the general idea. That's the thickness. This is the cross-sectional area times that. If I was to actually draw, right, there's my radius, and what is that cross-section that I've got here, right? I think everybody can see it. It's pi r squared, right? So the cross-sectional area that I've got is pi r squared. So force times cross-sectional area is the force that's tending to try to push these two sides apart, right? So we have the pressure force that's pushing them apart. What is the force that's keeping them together? Isn't that the force in the steel? In fact, if we looked at the force that's in this steel that's holding these things together, right? Just put it that way. That's going to be the shear right? The longitudinal, because we're going to blow these two parts out. Let me just draw the scuba tank here as to what we're looking at. We're looking at the two sides of the scuba tank, aren't we? And there's forces that are tending to push them apart. Those are pressure forces. And there's forces that are tending to keep them together. Those are our internal forces. And the stress that we have trying to keep that together is going to be the longitudinal stress. So if we know longitudinal stress is going to equal the force divided by the cross-sectional area, right? The cross-sectional area that we have here, so the force then due to that is going to be the longitudinal force times the cross-sectional area it's working over. Well, the cross-sectional area that it's working over, I should say the cross-sectional, let's see, it's skin. I'm going to put the cross-sectional area of the skin. So the cross-sectional area of the skin here is just 2 pi r, right? That's the circumference times the thickness. And all we've done is we've just taken it and we've laid it out, right, like this. And then the distance here is going to be 2 pi r, and the thickness, t, is going to be the other side. So 2 pi r t. Yeah, I've just undone that and looked at the cross section. So this is going to be 2 pi r t, right, times sigma sub L. All right, so now the force trying to blow it apart, the pressure force, and the force trying to hold it together, the steel force, have got to be equal to each other, right? Because it's neither exploding nor is it, it's just staying together. So I know that P times pi r squared has got to equal 2 pi r t times sigma sub L, right? So if I simplify that and solve for sigma sub L, I get, let's see what we can get rid of here. Okay, I'll use my other pen. We can get rid of the pi on both sides. I can get rid of one of those r's, and that cancels that out. Can't really get rid of anything else. So we've got PR divided by 2t. So sigma sub L is going to be PR over 2t. Let's circle that because that is our hoop. That is the defining equation for the longitudinal load. And so that's what it would do. If the longitudinal load is greater than the hoop load, the thing will blow up, and it'll blow its two ends, one end going that way, one end going this way, right? Well, that never happens, as I've mentioned before. So the longitudinal stress is PR over 2t. So what I want to do is I want to separate out that derivation of the longitudinal stress. And like I say, if the longitudinal stress is greater than the hoop stress, then the thing's going to blow both ends apart. And we've never seen that happen. So what we're expecting is that the hoop stress is going to be larger than the longitudinal stress, because we know that if I have a scuba tank like this, the way that it's going to fracture is going to be a crack along here, and that's going to be due to the hoop stress, right? And so that's what I want to look at now. Whereas over here, we were cutting it in half that way. What I want to do now is I want to cut it in half this way. Oops. I'm going to try to draw this in 3 dimensions. Here's my thin skin all the way around the scuba tank. right? Okay, so we cut it in half this way. You know, we still have a large amount of pressure area. We're going to do the same thing, right? Because this pressure in the inside is going to be working to blow the bottom and the top apart and to put a seam in it like this. That's what's going to happen. And of course, that is what's happened. What we'll find out in a second is that is exactly what's going to happen. I'm just going to cross hatch this to make it look a little bit better. Right? So that's the cross-sectional area that we need. And now, how I'm going to look at this in two ways to show you that it really is you know, what I'm doing here is pretty exact anyway. But I'm going to show you in two ways. So we're going to put a couple things there. So here is L, right? That's L. This at the end here, I'm going to say is D, because it's a diameter. The diameter of the scuba tank, right? It would be the diameter of the scuba tank would be right here as well, right? So we've got the diameter of the scuba tank. We could say that the diameter of the scuba tank is really 2R. I'm going to solve this in two different ways. But I think everybody can see that L is much greater than D. And even in the scuba tank, and it's much, much greater than T. So let's put that down there. L is much greater than D. And L is much, 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 much greater than T. Right? We know that D equals 2R. So we could even say that L is much larger than R, isn't it? Much, much larger. I put another one in there because I put only 2 in, and I'll put that in for R. So those are much larger, but let's look at the total cross-sectional area that we've got here. And I'm going to point out to you that we're going to make an assumption too. So I'm going to do this. I'm going to analyze this in two different ways. So first of all, the force to rip this apart, right? Well, that's going to be the cross-sectional area times the pressure. So I've got the pressure. I should make that I've made it a large P, so we'll call it pressure. P is pressure, so P equals pressure. Large P, small p, they all look the same. So P is the pressure times the cross-sectional area. And I think that everybody can see that the cross-sectional area, and I'm going to figure this out two ways. The cross-sectional area then is just going to be L times D, right? L times D. All right. So that's my cross-sectional area. That's my pressure. So I've got PL times D. PLD. But what is D really? Isn't D equal to 2R? So couldn't I say that this is really P times L times 2R, since we're working in R rather than D? Okay, that's one. That's to push it apart. How about what's keeping it together? And I want to analyze this in two ways. First of all, we can say, okay, well, it's really just this steel here that's keeping it together, isn't it? So it would be the hoop stress times the cross-sectional area of this steel. So we could say that this is really the cross-sectional area of that steel would be 2L plus 2D. Right? Does everyone see that? L, D. We do know that L is much, much greater than D, and it's much, much greater than R, right? But the circumference of this, the perimeter, is going to be 2D plus 2L. All right. So that's that. That's the actual times T, right? Because we've got the circumference or the perimeter now times the thickness. that we've got. All right. Now that's one way I want to approach the problem. Another way that I want to approach it is, well, we've said over here that L is much greater than D, right? So really that D is not, the L is the much larger part than D. So really L, I could rewrite this and I could say that this approximately equals sigma sub h times 2LT. All right, so I could say that. I could say that that's sigma sub h times 2LT because, you know, D is really going to be negligible. Now let's solve it that way first. Let's put these two equivalent to each other this way first. Then I want to do it the exact way just to show you that it'll still come out exactly the same. So if I've got P times L times 2R, and that equals sigma sub h times 2LT. What cancels out? Well, the L's cancel. I'll get the red one. Just a second. The L's cancel out. I think everybody can see the 2's cancel out. And so all I have left is PR over T. So I can say that sigma sub h equals PR over T. And in fact, that's usually the way that this is derived, right? And you can see that the hoop stress is always twice as great as the normal stress. Hoop stress is always 2 times the longitudinal stress. Does everyone see that? Hoop stress is always 2 times the longitudinal stress. And that way, the hoop stress always rips that open. Now, what I wanted to do, you know, I did that, but I wanted to actually take this and expand it out and sort of see how this would work if we equated the exact answer. So let's do it and simplify. So PL times 2R equals sigma sub h times 2L plus 2D. I think everybody can see the first thing that I'm going to do here is I'm going to take the 2 out of there. So that gives me 2 times sigma sub h times L plus, and then let's get rid of the D. Isn't that really 2R, right? Okay, so we can get rid of that 2. I'll get the red pen again. We'll get rid of this 2, and that 2. And then sigma sub h, if I write this out in the exact form, I get sigma sub h equals PLR divided by L plus 2R, right? And I know what you're thinking. You're thinking, hey, why don't we divide the numerator and the denominator by L? Actually, we got R in the numerator, so let's divide it by L, right? Hey, did I do that right? Let me just see. Sigma sum. Oh, you know what I forgot? I forgot the T. I got the T to LT. Yep. So that T has to follow that down as well. Haven't done anything to the T. So I've got L plus 2R times T. Let's not forget the T. All right, so what I want to do is I want to expand this out. I'm just going to do this so that I don't lose anybody in the algebra. And this is going to be LT plus 2RT. All right? So if I divide the numerator by L, what I end up getting is I get PR, right, over T plus, oh, wait a second, T, what am I dividing by? I'm dividing by L. So I'm going to get L out of there, then I get a T out of there, and I get 2RT over L. Is that right? 2RT, yep. Divide both, so I got PR. You know, I should have divided both by R, L and R. Why didn't I do that? I'll divide it by L and R, and then I get T over R, and then I get 2RT over LR, and I can get rid of that one. Okay. Yeah. Okay, so I'm going to have P over T over R, small number, plus 2, now the R's are going to cancel out, times T over L. All right? Now, that, and I'm saying it's going to approximately equal, because what am I really talking about here? 2T divided by L. Now, T divided by R, well, there's a certain thickness, it's about 1/4 inch, and I've got about 4 inches is R, right? So 1/4 inch to 4 inches is about a 16-to-1 ratio. How about this? Let's say that L is a meter, right? So what does that mean? That means, let's say 40 inches. So if this is 40 inches and this is 1/4 of an inch, it's 1/100th rather than 1/16th. So this really goes to 0, doesn't it? Does everyone see what the thickness compared to the length would go to 0? And so what I'm left with is I'm left with PR over T. So is this a valid assumption that 2L is the dominant thing here and that this really isn't needed? Yes. When you go through the whole thing, you see that this really is this is negligible compared to what this is. So PR over T is a valid assumption, and you can see that the hoop stress is always twice what the longitudinal stress is going to be. All right. Now what I want to do is I want to do an example problem. This is not a real hard example problem, but I want to show you what it is we're doing here. I want to drop this to the bottom of the Marianas Trench. So that is 8,000 meters. All right. Now every 10 meters, right? 10 meters equals 1 atmosphere of pressure higher. So at the bottom of the Marianas Trench, it's going to be 800 atmospheres of pressure. Now here's what we're doing. So we're going to put a scuba tank on top of a Navy ship. So the scuba tank is on top of the Navy ship, and it starts. So T equals 0. We've got it with 3,000 PSI. That's what I scuba dive. So that's what 3,000 you have in a scuba tank is 3,000 PSI. So 3,000, just to convert that back to the SI system, 3,000 PSI divided by 14.7 PSI, which is 1 atmosphere, times 101,000 pascals, which is 1 atmosphere, equals 20.61 megapascals. That's what the, did I get that right? Yeah, that's what the pressure is going to equal. Right? That equals P. That's the pressure, not the shear stress or anything like that. So that's the pressure of 800 atmospheres. 800 atmospheres equals 20 point, wait, did I do that right? 800 atmospheres. No, that can't possibly. What was I getting? 800. You know, I put the wrong thing in there, but let me give you the the right thing. So 800 atmospheres times 14.7. That gives me my pounds per square inch divided by 14.7 times 101,000. Sorry about that. That is 80.8. 80 point. Oh God. 80.8 times 10 to the 6 pascals. All right, that's what the pressure is going to be done. It equals the pressure. Now, the first thing we want to see is if I had, okay, so that's where the 20, okay, I'm sorry. So pressure of 3,000 PSI equals 20.61 megapascals. All right, that's where I want to start with. So I've got this, and that's a positive 20.61 megapascals. So this thing rolls off the deck, rolls, scuba tank, rolls off of deck of the Navy ship. So the scuba tank rolls off the deck of the Navy ship. What's going to happen? It's going to be compressed as it rolls off, right? So here's the thing. When is it going to get to zero stress? When or how deep do I go? This is part A. How deep do I go between when sigma sub h equals 0? Where does sigma sub h equal 0? So basically, I've got to overcome this pressure, don't I? I've thrown the thing off, so I want the pressure on the outside to be the pressure on the inside. Pressure on the outside, pressure on the inside. Let's just look at that. Well, that's 20.61 megapascals, and we know that we get 1 atmosphere for every 10 meters. So let's divide this out into atmospheres first. So if I have 20.61 megapascals divided by 101,000 pascals, that tells me how many atmospheres it should be. So 20.61 divided by 101,000 gives me 204 atmospheres of pressure, right? And we know that 1 atmosphere is 10 meters. So if I want to find out how deep it's going to be, this thing is going to be, so 204 atmospheres, I should just put this times 101,000 pascals per atmosphere, right? And so the atmospheres cancel off, and what I end up getting is, well, you know, actually I just did that, so why am I doing this? At 204 atmospheres, the depth of that is going to be 2,040 meters. You've already done that anyway. You're way ahead of me. 2,040 meters, it's going to go down. And at 2,040 meters, the pressure that was inside of it is going to be the pressure that is outside. So what's the differential in pressure across the boundary? 0, right? On the outside, I've got 204 atmospheres, right, in the ocean because it's 2,000 feet, 2,000 meters down. And inside, I've got 2,004 atmospheres. So what's the difference in pressure across that boundary? None, 0. Now, how much further can it go down before it's going to break? right? What is it going to be at the very bottom of the ocean? If we know that the maximum that it can take in shear stress is, in fact, why don't we find out what the shear stress? The shear stress is going to be 0 at this depth, right? So then from that depth and going down, it's going to be compressed. Instead of it being, out and then it slowly being brought back to 0 between the two, now it's going to continue going down to the bottom of the Marianas Trench, but it's going to be compressed, isn't it? It's going to start, the outer pressure is going to start to push in on that. Well, where do I have to go? If I know that the maximum shear stress for the steel, the maximum normal stress for the steel that I have is 400 megapascals, right? How much further down can it go before it breaks? We know the hoop stress is going to be PR over T, and we know that that has to equal 400 megapascals, don't we? We know that the thickness of the wall of that actually is, I'm going to say it's 1 centimeter. So the thickness is 1 centimeter. The radius we've always said is 4 inches. So 4 inches is going to be 10 centimeters, approximately, right? Because 1 centimeter is about, or 1 inch is about 2.54 centimeters. Okay, so about 10 centimeters, and so what does the pressure have to be then? So the pressure is going to be 400 megapascals times T, which is 1 centimeter, 0.01 meters, right? We're working in pascals, so it's a combination of primary units. So we've got to use primary units over here. Don't ever forget that. Always be the engineer and oh, wait. Well, of course, I put that in the bottom. Where's my correct pen? I'm just going to do this. I'm going to get rid of that because it's 0.1 meters, right? And then I'm just going to put a point down here and make that a 1. So that's 0.1 meters because the R is in the numerator. And then the centimeter that I've got down here is 0.01 meter. Everything's in primary units. We can figure out what the pressure has to be. This is the differential pressure, and this is the pressure. We've got to remember that we're already at 2,040 meters, right? So I'm finding how much lower than 2,040 meters I go before the thing finally cracks. And it might be at the bottom of the ocean. I don't know. Let's see. 400 megapascals times 0.1 divided by 0.01 gives me 4 gigapascals, right? So 4 times 10 to the 9 pascals. Now, we're at 2,040 meters already, right? We're going down to 8,000 meters. I wonder if we have the depth for that, right? Because it's going to have to, the pressure now is going to have to come up to 4 gigapascals before we get up to the 400 megapascals to cause that to fracture. So that's what I want to do, is I want to see how much deeper that's going to go. So additional, and I want to put this, I want to actually write this, additional depth equals 4, let's put a line through there, 4 times 10 to the 9 pascals divided by 101,000 pascals per atmosphere, right? So 4 times 10 to the 9 divided by 101,000 per atmosphere tells me we have 39,603 atmospheres. Did I do something wrong here? Let me just see. PR over T, 400 megapascals. 400 megapascals times, oh wait. Oh, that's why, you know, not having the class in front of me, everyone said, no, you're doing it wrong. Okay, thank God. And this one is 0.1, right? The T comes into the numerator, the R goes into the denominator. This isn't 4 times. Oh my God. So I'm sorry about that. I'm just going to cross out that 9. And this is 400 megapascals. So I'm just going to actually 400 megapascals times 0.01 divided by 0.1 gives me 40 megapascals. So 40 times 10 to the 6 pascals. Let me just get a sip of water for a second. Okay, yep, that. So let's go back to the additional depth that we've got, and I'm just going to get my corrector thing here. So it's not 4 times 10 to the 9. It is 4 times 10 to the 7. I'm just going to put 7 there. And so this also, so excuse me for a second, 4 exponent 7 divided by 101,000 pascals per atmosphere tells me that I've got 396 atmospheres. Well, yeah, okay, that's 396 atmospheres of pressure. I wanna correct that. So let me get rid of those. Excuse me. And I'm going to put 396 times 10 to the 1. So 396 atmospheres. So cross that out. Atmospheres, and that would equal another 3,960 meters before it fails. Right, 3,960 meters before it fails. So let's add those two together. So 3,960 meters plus 2,040 meters is still less than 8,000 meters. Did I say? Yeah, 8,000 meters. Still less than 8,000 meters, isn't it? Because that would be, I'll just tell you what it is, 3,960 plus 2,040 meters is exactly 6,000 meters, right? So 6,000 meters depth. That's what we got. And that's when it's going to collapse. So it goes down, and it's got pressure in it. And then the pressure that's on the outside equilibrates that pressure. And then it's going to keep going down, keep getting pressure and pressure and pressure. And then when it gets to 6,000 meters, 2,000 meters below the bottom, it's going to fail in compression. It's going to squeeze down to nothing and collapse in. The sides will start to collapse and break and buckle. And that's what's going to happen. That scuba tank is never getting to the bottom of the Marianas Trench. All right. stop. We got one more lecture, which is going to be on stress concentration factors. See you there.